Welcome to video lecture E8. This one is on matrix equations and spanning sets. It takes up where E7 left off. And the main objective here is to justify the equivalence of the following four statements for an m by n matrix A. So we're interested in understanding when the matrix equation, which we can view as a system of linear equations, ax equals b has a solution for every possible b in r to the m. So no matter what I put on as the right-hand sides, I should be able to find an x such that ax equals b. That's the question we're trying to answer here. That'll be equivalent to saying that for every b in r to the m, that it can be written as a linear combination of the columns of A, which is the same as saying that the span of the columns of A is all of r to the m, not just a subset of it. And that's, at the computational level, we'll see that's the same thing as saying that A has a pivot position in every row. So there are a bunch of things that were conceptual layers that we're adding on to the notion of solving a system of linear equations with which we started. And we can use this computational ability that we have with row reduction to nicely answer questions about sets of vectors, and we can use our understanding of row reduction to even prove things. So here we go. This is a reminder, so you should recall the three ways to view a linear system from the last video lecture, or from video lecture E7. So we've got an m by n matrix A, and we've got some length m vector B. So each of these n columns is a length m vector, and B is also a length m vector. And so the following things were equal: the set of solutions in r to the n of ax equals b, which could be also thought of as the set of linear combinations of the columns of A which give me B, so the coefficients that I put in front of them. And those are also the solutions to the augmented matrix given by A and then putting the vector B to the right of it. Okay. So the first question is, when is there going to be a solution? And so we know from row reduction that there's a particular condition that prevents us from having a solution, and that's really the only obstruction to having a solution. So do you remember what it is? It's exactly if we are avoiding having a bunch of zeros is equal to something non-zero. Because when you translate this back into a level of an equation, so if we have a row that looks like this, then we're basically saying 0 times all the variables. In other words, 0 is equal to something which is not equal to 0, and that can't happen. But so now I'd like to ask the question, is not just is there a solution for some particular b, but when is there a solution for every possible b, every possible right-hand side I can think of? And that turns out to be true provided that A has a pivot in every row. So let's look at an example here to see what kinds of things can happen. So here I've got a 3 by 3 matrix, so 9 coefficients, and I've got a column vector of 3 things that I'm trying to, you can think of it as I'm trying to write this as a linear combination of those 3 columns. Okay? So I do row reduction, and I get something that's in this form. But notice that what I've done here is instead of working with b1, b2, b3 as being some specific numbers, I'm just letting them be generic. And I'm seeing what happens with the row reduction. And it's pretty easy to see that the way to row reduce this is to multiply the top row by 3 and add it to this row to zero out this 3. Multiply the top row by -2 and add it, and you'll zero out this thing. And when you do that, you'll end up getting the matrix in this form. You don't actually need to go all the way to the row reduced echelon form, because you can see that these 2 rows are fine, right? Because this will say that x1 can be written in terms of x2 and x3 and a constant. This says that x2 can be written in terms of x3 and some other constant, because remember, this thing is just some constant that we've worked out in terms of the original constants here. But here we have 0, 0, 0. 0 is equal to some other constant. And that's going to control whether there exist solutions or not. The top 2 rows are okay. The bottom row could be problematic if this thing is non-zero. So this will be consistent exactly when -2b1 plus b3 is 0. Okay? So what does that mean? Well, here's a nice graphic for you. So you have to imagine we're in 3-dimensional space, and this green plane sitting in 3-dimensional space is exactly the set of all vectors that satisfy -2b1 plus b3 equals 0. So those are the only things that we can get. Those are the only That's the condition that we need to have on this vector b1, b2, b3 in order for it to be a linear combination of the columns. So what does that mean? Another way of thinking about it is that if I take every possible linear combination of these columns, I mean, these are all vectors in three-dimensional space, but somehow they all must lie on this green plane, on this two-dimensional subset. They lie on the plane and they never go outside of it, so they're living in flat land in three-dimensional space. Okay? So, and this kind of thing happens very commonly. So there are lots of linear combinations. If I want to get b1, b2, b3, there's not a unique way to do it. There are lots of different ways to do it, but I can't get every b1, b2, b3. So if I have a b1, b2, b3 that's sort of over here, there's no go. I won't be able to find an x1, x2, x3 that work. You know, later on we'll see that we can get approximate solutions, and that can be very useful in practical applications when exact solutions don't exist. But for now we're just focused on the exact solution. So if you're in the green plane, you're good, and if you're off of it, no good. So this leads us to the main theorem, the main point of this video lecture, which is, suppose we've got an m by n matrix. Then the following things are equivalent. For every, if I want it to be true that every b in r to the m, the matrix equation, this should be r to the m, not r to the n, sorry. The matrix equation ax equals b has a solution, and this should also be r to the m. For every b in r to the m, it's a linear equation of the columns of A. This is equivalent to saying that the columns of A span r to the m, and equivalent to saying that A has a pivot in every row. And this is bothering me enough that I'm going to see if I can fix this on the fly by turning with the closest thing I have to yellow here, turning that m n into an m, and turning this n into an m. And so now you see that I'm sort of like the weatherman here. I can't actually see exactly where I'm writing. I have to look carefully. So there are three things that are equivalent really just by definitions and algebraic manipulation. But this fourth one, that it has a pivot in every row, is very useful because it's something that, you know, you take your matrix, you check where the pivots are, maybe using some software if it's a big matrix, and that tells you if you have a pivot in every row, then you can write every value in r to the m as a linear combination. So here's what you might write down as a proof. Right? This course is not entirely a theoretical course, but you can't really understand the mathematics very well if you don't understand some of the theory. And so there are bits and pieces here that we'll be trying to get you to understand, because it'll actually make the course easier, quite frankly. If you try to memorize everything, it becomes overwhelming. But if you learn certain things that are true and then you understand how to connect them, then once you know how to connect the dots, you don't need to know as many dots. You only need to know a few dots scattered here or there, and you can quickly get to the other ones. All right, so 1 and 2 and 3 are equivalent to each other. That's what this if and only if sign means, just from the definitions, right? If I have an equation ax equals b, if there's an x that has if I can solve this for every x, then whatever solution I had for some given x is also the way that also gives me the linear combination of the columns that I need to write that same vector. And if I can do that for every vector, then that exactly means that the columns of A span r to the m. In other words, the span of those columns, the set of all things I can get as linear combinations, is equal to r to the m. And now, so the main thing to show is that this fourth condition is equivalent to being able to solve the system of equations. I mean, being able to solve, say, the matrix equations. So let's take a look at that. Suppose that 4 holds. Then I have a pivot in every row, and so that means when I do row reduction, I have A and then the augmented matrix, and then I've got B, and it moves to some row-reduced echelon form matrix U with some other vector C, just like we saw before. We had the B and then we had C, which was these linear combinations of the B sub i's. And if we know that U has a pivot in each row, then we can use that back substitution that I was showing you earlier to solve for each non-free variable. So each non-free variable can be written in terms of the CI's and the free variables. And so that means there will be a solution. On the other hand, if this is false, if there's not a pivot in every row, then when we put it in row reduced echelon form, if there's no pivot, that means that we have to have a whole row of zeros in the coefficient matrix, in the coefficient part, right? That's the only thing that can happen. So just like we had that row of zeros in the example, we'll have a whole row of zeros if there's not a pivot of that row. And then the question is, what's on the right-hand side? If it's all zeros equals 0, we're good. But because we're thinking about all possible values of b now, that means that we can get, well, we can get a bunch of values of c. And in particular, if we had Cm equals 1, then we'd be in trouble because we'd have that row would be 0 equals 1. Okay? But we know there has to be something with Cm equals 1 because we can work backwards. The beauty of row reduction is that every one of those operations is actually reversible. So because we can go back and forth, once I take the row reduced echelon form and I put something where the bottom row is all zeros, except I put, say, 1 as C sub m as the bottom entry of that vector. So once I do that, then I work backwards to convert u back to a. And when I do that, C will get converted back to some b, which is one of the possible b's, but this will be a b that has no solution because this AB augmented matrix has a solution if and only if UC has a solution. Okay? So that's how we can use some fairly simple reasoning based on our computational understanding to understand, and there'll be lots of examples where we do this, whether a set of columns, a set of vectors spans another one. So let's look at a few examples before we quit. So suppose we have the columns of this matrix in R to the 3. So we've got 3 columns, and we say, well, what do? We do the row reduced thing, and we get a row of all zeros, and that means that we don't have a pivot in every row. So this one has, so this one is not always solvable. And the span of the set of columns is not equal to all of our 3. Right? And this is the example we saw before where we knew it was actually, we could actually characterize it specifically as a plane in R2. Okay, here's another example. So if we look at this guy, we've got 4 vectors of length 3 if we think about the columns. So 4 vectors in length 3 ought to be enough to span all of R3. And if you take the row reduced echelon form, then in fact you see that we have a pivot in every row. That means we can always solve the matrix equation. And that means that, in fact, we can always find vectors in R4, right? Because we'd have to multiply this 3 by 4 matrix by a length 4 vector to get a linear combination of the 4 columns. But we can always do this in such a way that, that we get everything. And no matter what thing I pick in 3-dimensional space, I can always find a linear combination of these columns that works. Okay. Now here's another example that looks pretty similar, right? If I gave you these 2 matrices and just those 2 matrices and didn't tell you anything else, you might not, a priori, it might not be so quick for you to figure out like which of these sets of 4 vectors in R3 spanned all of R3 and which didn't. But you compute the row reduced echelon form, and which you can do using software quite quickly, and you see that, oh, okay, this row does not have a pivot. So if this row does not have a pivot, then it can't possibly span all of R3. And again, like the previous example, the span of these 4 vectors, they're all still going to lie in some plane in R3. They're not going to actually go outside that single plane. Okay, so this one is, so here, these columns do span R3, and then finally, these don't. Okay, so that's it for video lecture E8. Thank you for your kind attention.